In this topic, we're going to cover project number 2, process creation and shellcode execution. In this project, we are again going to use C types and the Win32 API. However, rather than injecting a DLL into a remote process like we did in project number 1, we are instead going to directly inject and execute shellcode. In project number 1, we also used an existing process ID in order to perform our injection. However, in this lesson, we will instead be starting our own process and then injecting directly into that. So let's start by importing from C types and also importing the subprocess library. We can save this. And now that these are imported, we can start working on our process injection script. And in order to inject into a remote process, we will need to again rely on and use a number of Win32 APIs. A number of which we have already seen and used, including virtual alloc EX, create remote thread, and write process memory, as well as some new functions, including virtual protect EX, which is quite similar to virtual protect, changes the protection on a region of committed pages in the virtual space of a specified process. So we can use this to change memory protection in a remote process, as well as some brand new functions, create process, which creates a new process, as well as queue user APC, which adds a user mode asynchronous procedure call object to the APC queue of a specified thread. So let's get started with defining and preparing the constants and functions for the Win32 API components we already know how to use. Let's prepare for kernel 32, size t, as well as lp str and lp byte. So these definitions will just make it easier for us when reading from the Microsoft documentation. And next, we need to start defining our functions. And we can copy and paste a number of these from project number 1. So we're going to again use virtual alloc EX. We're also going to use write process memory. We'll also need the security attributes class, as well as the security attributes and thread start routine variables. We're also going to need create remote thread, and we're also going to use our constants again. And now that we have our copy and paste out of the way, we also need to define some new functions too. So let's start with virtual protect EX. We can specify the archetypes here. So we can see that we need a handle. We need an LP void. We need a size t. And we need a D word and an LP D word. Next, we need the return type, which is a bool. And as mentioned, as part of this project, we are going to create our own process. And when creating a process, we could make use of the Python subprocess module. And we can use subprocess to create a process and obtain its ID. However, depending on our use case, subprocess can be limiting. For example, if we want to start the process hidden or to control which DLLs are allowed to be attached to our process, this can become more difficult. However, if you have a simple use case, you could say subprocess.popen, and we might want to open Notepad. And we could then get that process ID. We could execute this. Fix our typo here. We can see that Notepad started. And here we can see that we've started the process with process ID 9156. And we can check this in Task Manager. And here we can see notepad.xr with process ID 9156. However, instead of using subprocess, let's instead leverage the Create Process Win32 API. And as we can see here on MSDN, there are some new structures we need to define in order to use this API from within Python. So the startup info structure and the process information structure are both new. So let's take a look at these. So here we can see the startup info structure and the process information structure. So we can now convert these structures into our Python script so that we can use them from C types. So we can specify our fields. And there are a number here. Let's start converting these over. fix up a few typos here. And we can see that this startup info struct gives us a lot more control over our process creation. Next, we need to define the process information structure. So let's do that as well. Find the fields. And this structure will include important information for us in order to perform our process injections. And now that we have these structures defined, we can now also define the create process A function. And lastly, we need the return type. Is a bool. And now that we have our functions and structures defined, we need to have some shellcode to inject and execute. So we can make use of the Metasploit framework to create some simple Hello World shellcode. And so I've used my Kali VM to create my shellcode, which I'll now copy and paste. And you can see here, msfvenom-a-x64. Our payload is just a simple message box again. We specify the title of our message box, hello, and the text, which is world. And we specify the output format of Python because that makes it easier to copy and paste into our Python script. And now that we have our shellcode, we can set up a function, verify, to help with debugging. So this can help with our error checking. And now with that setup out of the way, we can finally get started. Our first step here is to actually create the process into which we want to inject our shellcode. So let's use create process A to do that. And in order to use create process A for our purposes, we also need to set up some variables using the structures that we already defined. So we can set up the startup info with our startup info struct. And we can specify the size of the structure in bytes. We can also specify some DW flags. To specify that we want to use show window. And then we can also specify show window. to be 1. And this is because we want to show the window as a normal window. However, if we were trying to be more malicious, we could specify 0 here to actually hide the window so that it's not seen. Next, we can set up our process information structure. And now we can actually start using the create process A function. So we can specify our process. And let's again specify the application name. And this is the name of the module to be executed. So let's use Notepad again. We don't want anything on the command line to be executed. We don't want to specify a structure here. We don't want our handle to be inherited. Next, we need to know our creation flags. Let's take a look here. And here we can see the process creation flags, which specify how the process is created. So let's copy over a few of these constants. Also specify create no window. And create suspended. Now we can continue with our create process A function. Let's create with a new console. And use the environment of the calling process. We don't need to specify the path because we used the full path already. Now we can pass in the references to our startup info and the reference to our process info. And these structures are going to hold important information about the process after it executes. And we can verify that there weren't any problems here with our process creation, but we should also be able to see that. We have a typo here. LPT str. LPT str. Another typo. By ref. And here we can see that again, we've started a Notepad process. However, this time we've used the create process A function from the Win32 API. And now that we've started our process, we have access to a bunch of information via our structures. So we have access to the process ID, the H process. Let's take a look at this structure actually. The handle, we have access to the thread ID. And a handle to the thread. And we can print this information out. Started process. Handle. Process ID. Thread ID. This should be DW process ID. And again, we can see our Notepad process as well as the specific information related to that process. And as mentioned, Create Process enables us to have more fine-grained control over how our process is created. So rather than specifying Create New Console here, we could also say Create Suspended, bit masked with Create No Window. And now if we execute this same script with those flags changed, we can again see information about our process. However, we no longer see the notepad.exe pop up on our screen. However, if we look in the Task Manager, we can see that our Notepad process with process ID 4128 has been started, and it's currently in a suspended state, which is congruent with how we started it. And due to the way we started the process, we also don't need to use open process anymore to get a handle because we already have one. And now that we have a handle, we next want to allocate memory in the remote process. And rather than creating suspicious read-write-execute memory like we have before, let's instead only create read-write memory. And as we know, we won't be able to execute code from within this memory unless we first change the memory protections later. So let's allocate some remote memory with virtual alloc ex. And we've used this function before, so let's pass in the handle, the size, which is the size of our shellcode here from buff. We want to have commit reserve. And let's use page read write memory. We can check that our memory has been allocated successfully. And if it has, we can print that out. We can execute this. And so now we've started our process. It's suspended and hidden from the user. And we've also allocated memory into that process's address space. And now that we have our memory allocated, we can now use write process memory to write our shellcode into that remote process. So again, we've used write process memory before. We specify the handle, where we want to write, what we want to write, and the size of the write. We can verify our write. And specify that we've written our bytes. We can execute this. And let's verify this using Process Hacker. So we need our Notepad process, of which there are a few. We know our process ID, 9568. And here we can see our memory regions. And here we can see our memory, which only has read-write protection. And here we can see what's written into this memory, FC48, FC48, through to 6C6F, CCF00. So our memory has been written into the remote process. However, because our memory is only read-write, we currently can't execute here. So let's use virtual protect ex to change our memory to page read execute. And depending on your use case, read-write execute memory can be an indicator to antivirus products or blue teams that something suspicious is occurring in memory. So let's try to avoid this indicator of compromise by using virtual protect ex. And we need to specify the handle to our process, a pointer to the base address of the region of pages whose access protection attributes are to be changed. So that's our remote memory address. Next, we need the size of the region whose protection attributes are to be changed. So that's the size of our shellcode. Next, we need the new memory protection option. And we want page execute read, which will enable execute or read-only access to this region of pages, which is what we want. And lastly, we need a pointer to the variable that receives the previous access protection of the first page. So we can put this here. And pass in this reference. We can check that this works. And print out our updated memory. And we can execute this. And we want to be using virtual protect EX, not virtual alloc EX. So here we have an error in our archetypes. And now we can execute this again. Specify this variable here. And now we can see that after fixing that typo, the memory protection has been updated to 0x20. And we can verify this. Let's find our new Python process, 8956. And here we can see that the memory region is now Rx. And now that we have created the process, allocated our memory, injected our shellcode, and updated the memory protections, our last step is to perform actual execution. And we can again use create remote thread to perform that execution. So we can say remote thread. We can pass in our handle. We don't need any security attributes. We don't need to specify the stack size. The start routine is our remote memory address. We don't have any parameters. We want it to execute straight away. And we don't care about the thread identifier. Verify our execution. And we can execute this. And here we can see again our familiar Hello World pop-up, which is coming from within this process that we've just started. However, this approach is not that interesting or exciting. This is the same way we finished our injection in project number 1. In Windows, there are a few different ways to perform process injection. So rather than just using create remote thread twice, let's instead use a different method in this project. Specifically, let's queue a new thread using queueUser APC. And we can use queueUser APC to perform the same code execution output as we just did with create remote thread. However, and again, depending on your use case, queueUser APC is usually a less suspicious function call. And as we can see here, queueUser APC is an asynchronous procedure call. So to use this, in this case, we need to be able to pause and suspend the thread ID, which will execute our shellcode. And luckily, we can do that quite easily, since we used create process A and have granular control over the process we are interacting with. And we have also already started the process in a suspended state. So since we already have that control, the only real change we need to make is to assign our procedure call to execute our actual shellcode to our suspended thread using the QUser APC Win32 API. And once queued, we just need to resume the suspended thread to gain code execution. And looking at the function definition here on MSDN, we can also see that we're going to need a papc function. So we can take a look at this. And as we can see on MSDN, this is an application-defined completion routine. And it defines a pointer to this callback function. And we need to specify this address when calling the QUser APC function. So let's define this function. We can use a cfunc type. The return value is none, and our argument is a pointer to a ulong. Next, we need to define our QUser APC function. Specify the arg types. A handle and a pointer. We also need the return type, which is a Boolean. And in order to continue our suspended thread, we also need to use the resume thread function. And we can see here, when the suspended count is decremented to 0, the execution of the thread is resumed. So let's define this. We only need to specify a handle. We can just specify a Boolean here. And now that these functions are defined, we can queue our procedure. And the function or procedure we want to execute is just the location in memory where our shellcode sits. And we also already know information about the thread from when we first started the process with create process A. So let's queue our thread. And we want to pass in our papfunc. Because this is the APC function we want to be called when the thread resumes. Next, we want the handle to our thread. And we can pass in none as the final parameter and verify this. And we can print out that we've queued our thread. We can verify this. Let's comment out our create remote thread here, because we no longer want to be using this function. Let's fix our typo here. And we can see that we've queued our APC thread. However, we don't have any code execution because our thread that we've queued into is still suspended. We can run our process here, 9140. And we can see this here in Process Hacker. So for our process with 9140 as the ID, here we can see our thread ID 5292, which is still in this suspended state. And so lastly, we just need to resume and change the thread state to be running. And once the thread is resumed, it will then execute our procedure call, which is our shellcode, and then terminate itself. So let's kill all these stale Notepad processes. And we just need to pass in a handle to the thread to be restarted. And we can print out that we're resuming the thread. And we can execute this. And here we can see our hello world has popped up again. We can also see that our process here is no longer suspended. And when we press OK here, we can see that the process dies because we've taken over the process's thread. So in this lesson, we learned how to create a process and use different techniques to inject shellcode into that process. Create remote thread is traditionally the most common approach to performing process injection and is therefore usually the easiest to identify and detect. So depending on your use case, you may want to instead make use of QUser APC if you're trying to be more stealthy and avoid common detections. But that's it for now, and in the next lesson, we are going to cover project number 3, key logging a system.